today? Well, we're going to look at this thing. This thing is called a radiacmeter, and basically it's a form of Geiger counter that uses an ionization chamber rather than a Geiger tube. Now, if one of these things registers radiation, something's really wrong and you're in a danger zone. Or you're like my wife and has had a radioactive trace, which actually I've had one before and I probably need one again for my MS analysis, or MRI scan rather. Anyway, this is a nice little antique. There's still quite a few of them going around. I think this is a Canadian made one. I want to get this running again, because I do have some sources that are probably just barely enough to actually trigger this. This actually doesn't have any sound output either. It shows only on the meter. There's no classic clicking like there would be with a normal Geiger counter. But I want to try and get into this and create a battery substitute. For those of you who are nerds in this regard, here's the ID plate that you can probably see. It shows where it was made, the Canadian Admiral Corporation. So let's find ourselves a screwdriver and get this open. I have a collection of good screwdrivers here. Probably that one will do the job. Go back over here. Now these used a bunch of batteries that are now very hard to get, or simply just are not in production anymore, or chemistries that are not used either. So now I need to try and get this open. It's sealed very nicely. There isn't much of a way to actually remove this without shoving a screwdriver in there. Alright, so this is our battery assembly. I'm not sure if you can see here, but it's supposed to use a BA 1391I/U, 2 in this situation, and then 2 B batteries in here as well, 1936U, plus another 2 batteries here. So I've got to work out how many circuits there are on this and work out what the voltages should technically be, and then I can probably make a substitute for this. I like the little Teflon isolated screws here. What are we looking at? We have 5 wires going in by the looks. Have a closer look here. We might be able to lift this little clamp up here a bit, because I'm going to have to remove that anyway at some point. So we'll pull our wire off our clamp here, and we'll have a look at exactly how many wires we have. So we have, there is a black underneath. So black, red, purple, brown, green, and white. So there's 1, 2, 3, 4, 5, 6. Yes, 6 wires. Okay, so I'm not sure how many circuits we're going to have with that. But I'm thinking what I can probably do is make a prototype board in here with several different regulators, maybe some lithium ion batteries, or maybe just some dry cell batteries in here to sort out the right voltage. And I am yawning. It's been a long day already. So well, for a start I want to pull this board off, and I'm going to map out which of these circuits are in series, because I can see a little bridge wire along here. So I reckon there's some series parallel oddities going on here. So I think my first job is just to map out what we have. Now, before some of you get onto Google, there is a substitute board for this. I haven't been able to find anywhere that I can actually purchase it, but there are substitute boards you can get for these. Anyway, I'm going to get this board separated from the back panel and see what's going on the rear of it. Alright, we've got these 4 little Teflon nuts removed. These nuts, by the way, are not threaded, they're just friction fit on there. So underneath this, we can see things are somewhat linked together here. There's some strange circuitry going on here. So I'm going to get a notepad and a pen and work this out. After I finish yawning because I'm tired. So I'm just going to take my time and map out what goes where. This is interesting. So yeah, so our brown, our white, black and our red all go through, except our green and purple go across the top, except for green goes round to there. So I think I'm just going to map out how all this works. So yeah, I'll be back in a few. Alright, so I've been busy. I've mapped out where all these batteries go. This is our black, by the way. But we have the 1391s, two of them are in parallel, completely separate from everything, and they go between purple and brown. Separate from all of that is this circuit. And this is where things get a little funky. So we've got two of these 1396 batteries, which I think are B cells. Now our red wire goes from the positive of that. We have two in series, and then we go off to black. So I know red and black is probably a primary power supply, which would make sense. So now what we've got is these two little button cells, whereas the positive of this one comes off the common negative and goes off to green, so that might be a pull down voltage. And then we've got here, this one has shares a common negative and shoots off to the white wire, so that might be a pull up. That might be for like meter range or something. I'm not entirely sure what's going on here, but this doesn't seem right to me. So it looks like we have 4 voltages. It looks like we've got 2 B cells here, which is going to be something like 3 volts, I'm going to guess, because they'll probably no doubt have been dry cells. So that will probably be 3 volts across black and red. And then we're probably going to have negative 1.5 volts and positive 1.5 volts, I'm going to guess. And then we're going to have 1.5 volts primary power supply. I'm going to guess that's probably for the high tension for the ionization chamber. So there's probably an oscillator circuit in there somewhere that brings that up to a high voltage. So I can get 2 of these voltages, so I need to go and research what these batteries are. I'm going to double check this because I'm not sure that this is right. Now, how I'm working out the polarity is looking at this board on here where they keep saying plus down. So most button cells, and I'll grab a modern one as a demonstration here. I've got one here. So most button cells like this, the plus terminal is the bigger one and the negative is the smaller one. So if you were to put a button cell, if we just drop this, take a button cell and put positive down, the only terminal that positive could connect to is this ring on the outer bit, and negative is going to connect to this top. So that would mean that these rings here are positive. So looking at this, when it says positive down here, in this corner here, this ring has to be positive. Now these are clearly marked. We can see positive and negative from those. So that's how I'm working out the polarities. This little odd setup with these cells is weird. I'm not entirely sure what's going on there. And this could make it a tricky power supply to provide voltage for. But being as they're battery supplies, there's a fair bit of tolerance in that circuit. So I'm going to go look up these batteries, look up what voltages they are and what chemistries, and try and make some sense of what's going on here. And this is also, I've checked that these are in the correct positions as well, and that they do definitely correlate with these studs. So I'm just double checking here whilst I'm recording, because that always makes me look like I know what I'm doing. Yes, so this has been hooked through the hole and there is a wire connection or a stud underneath that. And that's what I'm seeing here. There's our hook and there's our hole. So yes, I have identified those holes correctly, and they're at the funny angles. So I think I've got it right. And yes, those 2 terminals are folded on top of each other and soldered together. Our brown wire comes through and grabs that stud. So yes, I do have them correct, I believe, to the best of my ability. Let's go do some more homework. Okay, so in this short little jump cut, a lot has happened behind the scenes. So, firstly, I investigated a little further by actually opening the rest of the unit. And have a look inside here. Now we can see here, this connector here goes to the ionization chamber, which we have here. And the final inspection of January 28, 1969. and the actual unit itself. We have an inspection date on the bottom of the battery door here of August 1970. Oh, throat's a bit crackly. Now, electronically, there's not a huge amount going on in here. So it's mostly just some controls and some resistors and whatnot in here. Nothing actually really happening. Majority of the circuitry is going on in here, and I believe there is a valve in here as well. So most of the electronics is really in this unit. So ionization chamber and all, which is kind of handy if you are fixing these things in the field. You can rip the chamber out and plug a new one in very quickly. Now, the other thing that happened, I did a little bit of research and I found one of the original training manuals for field use for this unit, and I also over here found the original service manual for it, and it also tells me what the voltages are. So we have 2.8 volts, 1.4 and 2.8. So that was a push and a pull circuit. It also tells me where everything connects and what it should be. So yes, I'm going to have to do a lot more reading on this and work out exactly what should be where. I am having some trouble finding equivalents for these battery types here. These are old mil-spec battery numbers that are obsolete. The only reference I've found for them is on a manufacturer's website where they're going, for replacements, contact us. So I'm not entirely sure exactly what voltages those batteries are meant to be, but I think I probably have a solution right here. So a little bit more homework. I might print this out. I'm going to have a continue through this document. There's 42 pages full of stuff to go through, and I'm going to try and see if I can actually determine exactly what those cell voltages should be. Anyway, we'll be back in a moment. So whilst we're having a bit of a think and a bit of research, this is actually the ionization chamber broken down, and it shows a styrene box and an electrometer tube cathode follower. So while I was thinking it did contain a tube, the ionization chamber is in itself a tube. And it's got a graphite coating on it, which is why it feels cold. Now, this is a gamma only chamber, and I think it's designed to pick up gamma particles through the aluminium body of the counter itself. So only a very high level is going to really register on this unit. But and we have I think it's, I'm not sure what this resistor or what value this resistor is, but R1, it's in the mega ohms at least, we know that much. So yeah, it'll be interesting. So yes, I've got to do a little bit more homework and see if we can get this thing fired up. So I'm reading through the circuit analysis section here and looking at this section here where it states that there are two versions of the IM-174A PD. One that uses a single battery and determines all the voltages from that. About to get a postie visit, by the way. Anyway, that's my doorbell beam. Now, there is a second type here that uses 6 batteries, which is the one that I've got. So yeah, well, it says both versions use the same detector assembly or the ionization chamber. The other circuits, which have 0 control and function, are all separate. So that's the bit that I'm going to be interested in. So, yep, that gives us a bit more of a heads up. So let's go and see what else we can find out. Alright, so further to my research here, I have found the testing procedure where you check the voltages. And they reckon pin 1 on the red wire on switch S2 should be at 10.5 volts. Now, if we go back to my diagrams, which I am slowly updating here, with, of course, the battery numbers. The red wire here goes back to these series connected batteries here, which should total about 10.4 volts or thereabouts, which we'd expect to see on the red wire. So that is adding up. These are about 5 volt batteries or somewhere about that. So that gives me a good idea that I'm on the right track. It also means that the negative and the positive terminals on the meter should be about between 1.45 and 1.85 volts. And we can see here that that's pretty well in keeping with the voltage we would expect to see there. So battery volts might be a little bit high, and so that leaves us really only with the 2.8 volts of these batteries here. So I think we're getting fairly close, and if these are creating a bias of push-pull and they're about half off, 1.5 volts or 1.45 would be about half of 2.8. So that would be about right for those batteries if one is negative. And I have confirmed in the circuit diagram that this negative to the grid is indeed correct. And from my understanding of valves, which is limited at best, that would seem to be correct to have a negative grid bias. And because that is pulling, that would be about half of that. That would make sense. So I think I'm on the right track with the voltages. So I still want to do a little bit more double checking to make sure, but I think I'm pretty right. I'm going to go back through all these PCB things. I'm hoping there's actually a circuit diagram in here somewhere as well. There's continuity checks and all that sort of stuff in here as well. A full service manual for it. Oh, and it's saying be careful about the radiation with your test sources. Because you need to get an actual dangerous level of radiation to make this thing register any indicative reading. Just to reassure you guys, I'm probably going to sit a small test source right on the edge of the chamber here, so hopefully I will get a low level reading from it, but nothing that's really going to be a huge issue. I'm probably going to use some thoriated tungsten electrodes from welding rods. I've got just enough that might be able to trip a few ticks out of it, not that it makes any sound. Anyway, so I've still got more reading to do, and this is half this kind of a job, is reading stuff and learning and developing a solution. So I'm going to keep at it. We'll be back again. Alright, so where I was referring to radiation dosage, this unit here is good for between 1 to 500 Roentgens per hour. So to give you some idea, the background radiation around here is about 0.3 microsieverts per hour. Now, 1 Roentgen per hour is about 10,000 microsieverts per hour. So for us to even hit the low end of this scale, we're in dangerous dose territory. And yeah, so probably 20,000 times or 30,000 times the radiation level that is standard background level here. But yeah, 1 Roentgen, I wouldn't want to be hanging around that for very long at all, probably a few minutes at most. So certainly not in a concentrated beam. Anyway, that just gives you some idea of the scale of this unit. In fact, actually we can go over and have a look at the front panel of it to understand the exact scale. That's a little bit off balanced at the moment. So we are, yeah, a minimum reading is 1 Roentgen per hour. Well, this is rads per hour, so I might just check that Roentgens and rads are correct, although it is saying Roentgens in the manual for this exact unit, so I'm pretty sure Roentgens and rads are pretty close. So let's try and just do another little check here. Now, herein lies some of the problem we have with maths here. So I've gone rads a second instead of rads per hour to microsieverts per hour, and got 36 million. So dividing that by 60 to get rads per hour, which might not strictly be how the maths work, is still 600,000 microsieverts. So I could be wrong in the way I'm doing the maths there, but either way, the point is this is in a whole different category of radiation. So this would be useful for, say, next time me or my wife, for instance, gets a radioactive trace. Cut to a clip right here as to why that would be useful. And yeah, what we might do, we'll switch to the other counter here, and we'll see when this. So she's certainly slightly radioactive, and I think it just went in overload. So yeah, I'm glad we gave the apprentice a day off for the day. So yeah, and she's still, you can probably tell when she walks away. So at this point, this is going to be handy to determine when a safe time is to bring the apprentice back home. Well, she's now 2 rooms away and still detectable above background. And so yeah, you can see from that when you're full of technetium, as my wife was in that clip, you're spewing off gamma particles left, right, and center. But it's got a very, very short half-life. So yeah, we should be fairly good not to actually need this. If we do, we've got bigger problems. So I'm going to focus on trying to at least get the power supply correct for it. Okay, well, several weeks have passed since the last clip, and I put this pretty much on hold. I had a few things happen. My financial manager had a bit of a medical emergency, so I've been dealing with all that. But I have stumbled across some more information about this radiacmeter. Now, I have this circuit diagram here I found that shows the wiring of the battery, which has helped me confirm things. So I've highlighted each pair of batteries in a different color and which color wire it comes out to. I then went through the schematics I've got and found the holy grail. These show the battery numbers and the voltages of the batteries, and also how they're interconnected. So that further helped me confirm it. So from that, I've been able to simplify my schematics quite a bit. So I now know that BT3 and 4, they're both 1.34 volt batteries, and they're in parallel, making 1.34 volts between violet and brown. I now know that I have two pairs of series connected batteries here with a common ground, and so I'm looking at where are we? The black wire, which is, my handwriting is horrible. I've got MS, guys. It's screwed my dexterity, so you'll have to deal with this. This is our black wire, and BT6 is a 5.2 volt battery in series with another 5.2 volt battery, meaning we have 10.4 volts. In common ground with that, we have BT1 and BT2, which are both 1.34 volt batteries, and they appear to be in a series circuit as well. So we have, yes, it's just in a funky way. So that is positive to negative to positive. So we should have 2.8 or 2.68 volts across white and green. So that's good. I understand there's a bit of variance. Some of these like bump this almost as high as 12 from the look of things, but that really helps me. And so yeah, we've got the full schematic here, how the whole thing's laid out inside, which is actually really simple. So and it actually, in this bit of information I've been given, it's a complete workshop manual. It shows all the chokes and the resistor color codes and every little detail I need. I could probably build one of these from scratch now, but crucially, that gives me an idea. Now I'm going to go find my idea. Alright, I've been looking at possible ways to power this thing, and I've come up with a few different ideas. Now, originally I went digging through my stuff to figure out how I'd get 10 volts. I found an LM7810. It's a 10 volt linear regulator. That certainly might get us close to 10.4 volts. And then I realized that I had a look on the net, and somebody somewhere recommended using a 9 volt battery. And I think, you know what, for what that side of things is doing, the 9 volt battery might be enough. It's already being stepped up for the chamber voltage anyway, so a 9 volt might be fine for that. And that side of the circuit is pretty well independent, aside from the common ground here. Now, I thought for BT1 and 2, I was going to try and get, I've got a 3.3 volt regulator here. This is a tiny little board. I've got a bunch of these. Not real high current, but that'll give me 3.3 volts, and through a half volt drop through something like a, what are we at? What a 1N914 diode, for instance, would probably give us about a half volt drop, bring us right down about 2.8 volts, which would be very close to 2.68, especially with a bit of load on. So that seemed to be an option. And then I thought, you know what, I can probably just whack two LR44 batteries in there. They're 1.5 volts each. Not quite as much current as a mercury battery, but under load they might drop down to about 1.34 volts. I think these might be nominal cell voltages, not actual cell voltages when they're, you know, brand new batteries. Now for this side of things, for BT3 and 4, while they call for 1.34 volts, and my microscope's just turned off, you know what, under load, and that is the high current circuit, a couple of double A's would probably drop down from about 1.5 volts down to probably about 1.34 volts, or I could even just whack one in there. A couple of rechargeables would be 1.2 volts, and that's similar as well. So I can probably get close to this using batteries, and I think that's probably the more sensible way to go. I'm still going to be undervoltaging by about 1.4 volts, but I'm erring on the side that these things were designed to run off batteries, so they're going to be a little bit voltage tolerant, like when the batteries start to get down. So I think I'm going to come up with a solution that uses batteries. That's also going to be technically more simple as well. So yeah, in light of that, I'm going to go find myself some battery holders. Now, before I go and buy battery holders, I need to actually figure out what batteries I'm going to use. So I've translated my previous diagrams into one very simple diagram. So in place of a 10.5 volt battery, I'm going to use a 9, and a standard 9 volt battery like a smoke alarm battery should do the job. And that's going to be roughly equivalent to the stacked mercury cells that they would have used anyway. In place of, which cells have we got here? This would be in place of both BT3 and BT4, which were a parallel pair of 1.34 volt cells. I'm using either a C or a D cell battery. I'll probably fit a C in that cabinet. I probably won't fit a D, so that'll probably be what I end up using. I could use a AA if space restricts. This is really only going to be for short-term use. So anyway, that would be 1.5 volts in place of 1.34. Now, in place of the two little baby reference ones, the balance batteries, which were BT1 and BT2, I'm going to use a pair of AAA batteries in series connected, but I'm going to have to tap off the series connection link on the back here, and I've got my camera tripod on my page, so this is a bit difficult here. So that link is going to go all the way back around to the black wire, which is ground, and then we're going to go off to the green and white wire from there. Now that will be 3 volts in place of 2.68 volts. And it's a bit confined on my desk at this end, so I'm bumping the camera. So I should be fairly close to the voltages. And from this sort of thing, this is to run the calibration. So this is a bias for the tube. So there is a potentiometer involved in balancing this anyway. So that slight variance in voltage will be fine. Mercury voltages did tend to waver a bit with voltage anyway. So I think this should be the best, closest variation I can get on that circuit that's simple. And it's going to run off some commonly available batteries. So that'll be nice. So it's off to my local JCar store to grab, in fact I've got a stock of 9 volt battery clips already, but I am going to need a C-cell holder, and I might get 2 individual AAA holders. And that actually might be all I need. It might be that simple. Anyway, we'll be back with some bits. Alright, I was going to sneak down to my local JCar shop, but I thought I'd better check to see what I had hanging around in my collection, and as it turns out I have a few battery holders. I had an unwholesome amount of 9 volt battery clips, and I used very few of them. So I've got a new 9 volt battery, I've got some new AA's, which should work. Now I've got a 3 AA holder and a 2 AA holder. So if I bridge out one cell of that, that should be fine. And that might actually give me a nice little link wire that I can hop off the side with for BT1 and BT2. These two should, or I might even be able to configure that to hook them in parallel, which will be what I need to do for the other ones. I was going to do 2 AA's for that one. So yeah, I'll work this out. I'll come up with some wiring, and we might test this with battery clips fairly soon. So the wait might be over. Okay, so it's smoke test time. So these two batteries correspond to BT1 and 2, making a 3-volt series connected string with a center tap off it that goes back to ground, and that shares a ground with our 9-volt battery, which is substituting the 10.5 volts. We have a single AA battery here. Hopefully I've connected that correctly with that battery holder. We'll find out very soon. And I think we're all right. So I think we can change our camera angle, and we're going to go over to our radiacmeter and see if we can calibrate it. Alright, so it does help if you read the instructions a bit here. So I've got to turn this off. I have to hold the 0 knob. I have to turn this on and turn the knob up until we 0 it. So we hit that. Then when I release it, it should come back to a level. Then we should be able to go check, and that should put us somewhere near the check level. I think I bumped the 0 knob. Let's try this again. Let's re-0. Alright. Now let's do a check. We're a little bit over our check limit, but that could be because our voltage is a little high. But we are getting some normal behavior out of this. I might see if I can find, and that could be this calibration knob here too. So I might find something slightly radioactive and see if we can make it do anything at all. So under the lift here to service, there's a little tiny grain of wheat globe, or not grain of wheat, but very small incandescent globe that's obviously meant to work with a mercury battery in there. So that's just our dial illuminator, nothing fancy there. So we still need to work on calibrating this and maybe lifting our voltages somewhere a little bit, or dropping them. I'm not sure which. But yeah, that could be our bias voltage that's not quite right there. So we'll look at that in a minute. Now I'm going to take a slightly more sensitive counter here, my little Radex, and I have a stack of thorium tungsten electrodes here. They're not probably hot enough to really get a real reading out of this radiacmeter, but they do put out gamma particles. So we might be able to see a reading out of that. One thing, I'm not too familiar with these things. I'm not exactly sure where the detection area is, although looking at the chamber, it's probably right on the end of the unit. So if we can get this thing on again. Oh, we've got our check range, so we are still actually functioning here. So I'll stick these guys right over the end here, hold them there for a little bit and see if we get any sort of particle count on it, if it raises up at all. So then again, it's got to be extremely radioactive even to get to notch number 1 on this. So I am seeing a slight increase on that needle. Ever so slight. I'll leave it sitting here for a couple of minutes and we'll come back. Alright, I've got a little bit of backlighting here to help. I've actually calibrated this till it sits on the 1 just to make it a little easier to see. Now, it's at a funny angle because I've taken the ionization chamber out and it's sitting on the bench. Because I'm trying to sit these thoriated rods really anywhere as close as I can to the chamber to see if I can influence it even in the slightest. Which, with this test source, I'm probably not going to be able to. So yeah, I do have some americium, but it doesn't put out a lot of gamma particles. I might try a bit of uranium glass and see what happens. Alright, now I've got this uranium glass car here, which is probably the hottest thing I own. And I'll just put it up next to this and see what we get off it. Still not a huge amount of radiation. This would have been handy to do when my wife was just out of radiation treatment, or not treatment, they gave her technetium as a radioactive trace for an MRI scan, but she was as radioactive as blazes and throwing off gamma particles for a couple of days, so this would have actually registered something at that point. In fact, I think I can probably find a clip of that video to insert here somewhere, but we'll see if I get round to that. So yeah, I'm not seeing any movement on that needle at all, but that's also not surprising given the sheer volume of gamma particles that's required to even move this needle in the slightest. So I'm not sure if the ionization chamber is working yet, but we might have to bump it up to 10 volts somehow. But I'm going to leave this here for a bit and see if my needle moves. Alright, so it's off at the moment, and we are going to do a normal startup procedure and dial till we zero it. I'm going to go from here. Oh. Yep. I'm going to let it settle, then we're going to do our check. See if we can bring our check back into normal ranges. It's a bit hard with the lighting level here and the angle that we need to use, but let's try something like this. At some point I'm going to have to improvise a backlight for that scale. We can probably see a little better here. Okay, hopefully we can see on camera. So I'm going to do this a little bit quirky. Now actually I might be able to hold that and then adjust the bias till we can get our check range normal. Flat blades, I hate the things. Get right in the middle of our check range. Let's drop her down and we should be calibrated. Okay, so now when we go check at this voltage, that's our battery check. So that should be on the low side, which is what we would expect for 9 volts when it expects 10.5. So that's good. So I'll put that little do not remove cap back on. There's big white text on the bottom here that says do not remove cap. And this is why, because that's your battery level calibration. So I think it's going to function like this actually. So for the moment, it's late at night. I'm interrupting everybody. So I'm going to park this for the night. I'm going to turn it all off. Yep. That should be off. Yep, that's definitely off. Okay, turn it off. I'm going to park it for the night, disconnect all the batteries, and I'll make a proper battery replacement in the morning. Alright, well, some progress has been made. I've removed the original battery holder out of the unit. I'm keeping that in case I ever need to put this back again. The wires I've chopped as long as humanly possible so that I can restore this to its original state if we need to. The batteries are held on with some super strong mounting tape, and I've attached these wires with a heat shrink so we don't have a short circuit event. The next question is whether or not I'm going to be able to fit everything back in here with the wires all like this. So let's see what we can do. Well, it fits, but a little bit of lip on here, but that's okay. This is for display purposes. But we can see here that our dial roughly works here, so we're doing pretty well. And I've got to zero it actually, so we'll turn that off. We will zero things and we'll leave it run like that. Okay, so and we can check our battery volts here. Should be on the low side, which is what we expect, because we're running about 1.5 volts down. Now I still need to do something about the light in here, the illuminator, so we'll do something about that in a moment. Alright, for me this actually looks a whole lot more interesting. We are going to give this dial a bit of a clean up. I've got some isopropyl alcohol fitting around, and we'll give the top of this a bit of a clean up as well. But yeah, this actually looks quite nice with the shroud off, so that does allow me to actually work on this. I have no grip because of all the hand sanitizer that I've been using, but yeah, but these screws would probably have to go back in. They're quite long screws and they're probably holding the dial in as well. But yeah, I'll probably put the shroud back on so it stays with it. But yeah, if I go to use it, I'll probably take the shroud off. Alright, now isopropyl alcohol at the moment is kind of hard to come by because of the virus stuff, but things are starting to calm down a bit in Australia, so at least in Victoria anyway. So it is possible to actually get some now. I'm getting some of these glue marks and stuff off the top here. It's looking a lot better than it was. We'll go and just give the dial a bit of a wipe off with a bit of IPA, just gently. Don't want to scratch the glass. Make everything look just a bit cleaner. I'm going to let it soak on that glue for a bit just to try and soften it a little bit more. We do have a few sticky handprints on the side, so let's a bit of a wipe down and just generally make it look a bit cleaner. But we do look a lot cleaner and shinier now, and we can probably start to put this back on again. We'll be putting this on, and then we'll find somewhere that we can test it. That'll probably be in a different video, because this one again is getting quite long, and we want to finish it up. Well, that's it for the radiacmeter, the IM-174A/PD. So it functions. I'm not sure how well yet, but there'll be another episode on it. So I hope you enjoyed this. We'll see you all in the next video, and we'll move on.